Time-Independent Schrödinger Equation. What? If you are wondering what I'm talking about, that's what you're going to learn today, guys. In this episode, I'm going to introduce the time-independent Schrödinger's equation to you. I'm pretty sure you must be already familiar with time-dependent Schrödinger's equation, but this is the subversion of this, which is yet powerful. And though it is a subversion of our previous equation, which is time-dependent Schrödinger's equation, this is still very useful, guys. To start with 1D potential well and to sometimes understand tunneling properly, we have to rely on time independent version, guys, because time dependent version is a bit more complicated option, right? So we have to go with time independent Schrödinger's equation. But what exactly time independent Schrödinger's equation is? So how can you, first of all, you might be wondering, how can I write just as I wish a separate equation called time independent Schrödinger's equation? No, don't worry. I'm going to start with one of the tools that we already have. It's not just a tool, it's a particular powerful equation which mostly governs the quantum mechanics that we already know, which is time dependence Schrödinger's equation. But for simplicity, guys, we have been dealing with 1D equations yet so far. But I think later, when you are ready, I know when you are ready, I can transfer your knowledge, or I can convert everything to 3D version of all of these equations. There's no hurry. Wait. Right. So we already know the time independent version of Schrödinger's equation, which is time independent Schrödinger's equation. But let me write it again. The 1D version of this one is I h bar da bar of phi xt, and we already know what phi xt is. That's a wave function over da bar x. And if you are a new viewer, guys, I strongly encourage and I strongly motivate you to watch my previous set of videos. I think all the prerequisites are there, prerequisite tools are there in my previous videos, and start from scratch. That could really be helpful for you to understand quantum mechanics. So here, guys, I'm going to first of all lock the base and the foundation in your mind, and then you'll be able to pick quantum stuff later on easily. So that's my major role, and that's my major motive here, right? Right, so let me write the time dependent version of this Schrödinger's equation, which is I h bar n is equal to minus h bar squared over 2m, right? And this is, so sorry, here my time version of this one, I made a slight mistake, sorry. I h bar da bar phi xt over da bar t, that's the time derivative of this. And here we write da bar squared, here phi xt over da bar x squared plus v. I deliberately take vxt here, guys, and it's actually potentially is a function of time and x that depends on the spatial part as well as the time part, uh, unless it's a special condition, right? So then here it is phi, again our xt, well known renowned equation, right? But now what if we can write, or we already know that wave function, guys, depends on both x and t. The spatial part of the equation is x, and x represents a spatial effect and t represents a time effect. So it is a function that depends on both x and t. What if we can separate them and write this like this? Imagine now, what if I can write ax and here phi t. So now this function, which is a wave function, is written as two separable solutions. But is this valid under every condition? Not really, guys. This is not valid under every condition. That's the problem. But if you can write it like this, that could be quite useful. So that's what I'm going to find out. So I'm going to find out, first of all, under which conditions we can write separable solutions. Right. I'm going to let you know, in advance that you can only write separable solutions like this, guys, when this V, which is potential, doesn't depend on the time, when it is a function of x, in fact. Right. So if you can write it like Vx, that's a favorable condition for the wave function to be separable like this, and to for the wave function to separate and just show up as a function of x and function of t. So, but why? Sometimes you might be wondering, if you're someone like me, I never satisfy with just statements. I really want to dig into the tunnel and find out what exactly the reason for that is. Hold on, I'm going to show you now. So what if I just write, now I'm going to plug this separable solution. So I'm going to I'm going to consider that I can write, this can be written as two separable solutions, and I'm going to go ahead and substitute those values, and not values, these functions over here and over here, and see what will we end up with. Let's see. Right, so now here I h bar we have, and here da bar, and here ax. But oh, it's pretty annoying if I write x and t. You are smart enough to understand that I'm not going to write ax and phi t, but instead I'm going to leave them like this: a phi over da bar t is equal to now minus h bar over 2m here, and here da bar squared a phi, and here da bar x squared, plus here we have v, and still it's a function of both x and t, and here we have now yeah, phi, oh, not phi anymore, it's a phi. Right, now you can clearly see that here now da bar t is always seeking for functions depending only on the time, and all the others are treated as constants. Now here the only function that depends on the time is now phi. So a is treated as a constant. So now you can take a out of the bracket. So I will end up with minus ih bar, right? Here even a is a part of this now, and da bar phi over da bar t is equal here minus h bar, same as what I did here. Even now here phi is a constant, as a is the only function that depends on x, so I can take phi out of this. So I will end up with h bar squared phi over 2m, and here da bar squared a over da bar squared, oh, da bar x squared. Right, and we have two more options here now: vxt, here a phi. Okay, now let me take, I need some more space. Right, now this equation, I'm going to go ahead. Now I have this equation a h bar, and here da bar phi over da bar t is equal to minus h bar over 2m, here da bar squared a over da bar x squared, plus v here xt and a phi. What if I go ahead and divide this equation? Let me take it as 1, and this entire 1 equation, guys, I'm going to divide it by both of these functions phi and a, and let me check what I will end up with. So here I will end up with 1 over phi, and here da bar pi over tau by t. And here I will end up with, oh, where's my constant? Where have it gone? Where has it gone? No, we have to have it. So which is phi here. Oh, I can't forget about it. Sorry, my bad, guys. Then here minus phi. And when I divide it by phi a, I will end up with minus 1 over, yeah, this time 1 over a, which is the function that depends on the spatial part of this, and here h bar squared over 2m, you can keep it as it is, and here dou bar squared a over dou bar x squared, right, plus v x t and a phi. Oh, not a phi anymore, it's now as, yeah, v x t, yes, as you have divided by both of these functions, so we end up with here v x t, right. So now, interestingly, guys, I can see that there's a now there's a statement, there's a mathematical equation that we have just derived, but this part of this equation depends only on the time. Wow. And this part of this equation depends on the what, the spatial part. You can say x. I'm a lazy guy, so I write x, but you should be able to understand that it's the spatial part of this. But this is the problem, which depends on both x and time. Both x and time, right? So now here we factor that option depends on both x and time. So now I have to do something about it, guys, right? So what I'm going to do is now what if now this is x and t, it depends on both x and t, right? Now what if I just take that if only this one depends on time, right? Only this factor depends on time instead of, sorry, my bad, only if this factor depends on x instead of time, guys, I can write something meaningful. Because then, guys, there is one side which depends on time and there's another side which depends on x. So there's no way to write this relationship unless or only if that both of sides, for example, the right side of this is equal to a constant and the left side of this is equal to a constant. So that is a very favorable condition for us to write separable solutions, guys, right? But here now there's no way to write separable solutions. It's very complicated, guys, because there's a function which depends on x and t both, so therefore you can't it restricts, it simply doesn't allow you to write some simple to just functions that depends on x and t. So what if I just change this a bit, and what if I write this only depends on x, right? So then this function depends only on, and I'm going to transform this into vx, that allows you to write something very meaningful. Reason is now, guys, this depends only on the, and this entire right side depends only on the x. In the meantime, the left side depends only on the time. So now let me modify this equation in this manner here. Now even here I forgot to write h bar. It doesn't matter now, those are minor mistakes. H bar is all still a part of this one. So now here 1 over phi and h bar, here dou bar phi over dou bar t is equal to, here you have minus 1 over phi and h bar squared over 2m, and here dou bar squared a over dou bar x squared, plus here now there's a function that depends only on vx and right time. And now you have this side depends only on time and this side depends only on x. They can't ever be, I mean, you can't just get two equal equations only if these two sides are equal to one ultimate constant, and we recognize those constants to be energy, guys, because we know that this is the Hamiltonian at the end of the day, right? even we are dealing with Hamiltonian here. So that is something equivalent to energy, right? Okay, nice. Now, I need some space. Right. Let me go ahead and write something very important. Now we have two important equations. Two important yet powerful equations, right? The equation number one is this equation, which is right, which is this. Now I can write 1 over 5. Right, guys, I think now here then, oh, I think I missed the I part here, guys. Mind my mistake here. So here we can't, so everywhere I should replace I here, and even I is a part of this, and even I is a part of this, sorry. And even I think, if you don't mind, replace this I, guys. I think I missed that. It's okay. Then even in my video, I'm going to mention it. Right. So anyway, now here I can write spatial solutions like this now. Right. So let me go ahead and write then 1 over 5 I h bar over W 5 over W t is equal to energy E. And you have another one minus 1 minus 1 or yeah 1 over A, 1 over A here h bar over 2m and here W squared A over W x squared, W x squared plus Vx is equal to E. Believe me or not, we have just derived the time-independent Schrödinger equation. Here you can have the time indication. Sorry, welcome to the time. It's time to welcome you to the time-independent Schrödinger equation. This is what the time-independent version of Schrödinger equation. Because, guys, anyway we write about energy here, then here energy here in this equation is equal to what? Minus or you can, yeah, so move this term to other side now, right? So then I'm going to, yeah, we are on the verge of proving this equation. Now what if I just multiply this one by A? So I will end up with, let me take this equation at equation number 2 and get the product. So multiply it by A. So we will end up with minus h bar over 2m and W squared A over W x squared plus Vx Ax is equal to Eax. Guys, this is what we call the Schrödinger's or time independent Schrödinger's equation is TISE. Because here we have already got rid of time section or time dependence of this one. So this is a particular equation that doesn't depend on the time, right? So we have filtered the time section of this one, but time part is already here on the other side. So mostly what we do is we use time independent Schrödinger's equation to find the energy eigenstates. So I'm going to write energy eigenstates carefully now. And in the meantime, we can use this relationship here, which you have on the other side, to get the time dependency of this one, in the sense which phi, this function which depends on the time, right? So I'm going to dedicate this part or devote this one to proving the time dependency or time dependent function of this one, which is phi, right? So I need to have some space, but keep that in your mind, guys. This is very important. This is the time independent Schrödinger's equation, right? And okay, good. Let me erase this part. Right. Let me pay my attention to this. Right. So which is this one is equal to energy. Right. And now here, yeah, so now I can say pi is equal to, when I rearrange this equation, I will end up with something like this. Pi is equal to here, yeah, I h bar, or E phi is equal to I h bar dabba phi over dabba t, dabba phi over dabba t, and here this is a phi that depends on the time, function that depends on the time, and furthermore, and also for simplicity, now we already know that this depends only on time. Phi is a function that depends only on time, and even this one, this one is also a function that depends only on time. So I don't really want to keep the dabba terms anymore, so I can just go ahead and write here IH, here d phi over dt, and now I can write d phi over dt is equal to here E phi is a function that depends on time again, and here h bar, sorry, over h bar here on the other side, and here I, and even here I, then I h bar, and here I keep it as it is, and here this is a function that depends on time, phi t, right, and even this is a function of time, right, and furthermore I can write d phi over dt is equal to, I don't like to keep this in the denominator, so I'm going to multiply it by I. So here I, so I will end up with here now I squared, here I, and here I squared, so I squared is minus, so that will end up with minus E I over h bar here phi t. Guys, this is valid only when several times we have come across these sort of relationships. So this is valid only when, this is not new to you, right? So this is valid only when, right, only when this phi t is an exponential solution. Phi t is an exponential solution, then only we can write carefully crafted this, we can write it as a solution of this. So you can just define that here this is an exponential. Now we need to have, and here this is the function itself, guys, and here this is ei over h bar. So what if I write it like this, exponential minus, right, e I over h bar, ei over h bar times time. That's a very important solution. So that depends on the time, and if you get the first derivative of this one, you will end up with this one, minus ei over h comes to front, and even I can show you, but I think now you are smart enough to understand these sort of calculations. So now this is a very comfortable solution, because when you get the first derivative of this one, right, e minus ie over h bar comes to the front, and again e times minus ei over h bar times t will remain as it is. So now this is the time function, and guys, now you can actually write your final phi xt, our time option. Shall I write it on the other side? I need some space. Let me erase this section and replace it by what we have already found out. Right, now we can write separable solutions, guys, like this, separable solutions. Now number one is phi t separable solution. Phi t has just been identified. It's here minus I e I t over h bar, right? And phi ax should be found out, guys. You have to use Schrödinger's equation, which means the time-independent Schrödinger's equation can be successfully used to find the time separable solution. And here now you can finally say that phi xt is equal to ax and a to the power minus I here energy I t over h bar, right? So now we have just written the time or the separable solutions, and remember that, guys, this is an energy eigenstate. Energy, this is called a stationary state, guys, so this is going to play a very important role later on. This is called an energy eigenstate. We already know that these phi x t stuff are eigenstates, but none of the states, not all the states are eigenstates. Sometimes, right, we will come across some other strange states too, right? So when you come across, this is something very important that I want to show you guys, right? So when the potential remains constant, in the sense when the potential, not the constant, actually, that's my brain freezes, so that's wrong. When the potential is not a function of time, when the potential is only a function of x spatial part, you can write separable solutions like this. Your wave function is separately a function of ax times function of a spatial part and function of time. So then here this is called the energy eigenfunction, eigenstate. Most importantly, if you ever get the probability density of this one, you can clearly see that, guys, you already know that when you get here, this will not change, it's ax squared, but here this is, you have to get this is an imaginary exponential. So when you have imaginary exponential and squared, when you get, you have to multiply this one with the plus. So I have already introduced this to you in my previous video, and this is called the conjugate, complex conjugate. So that's a plus one. So now this part will be 1, because when you add them together in the indices section, right, when you add the indexes, you will end up with 1 here. So now I want to tell you one important thing. If this is an eigenstate, energy eigenstate, guys, the probability density depends only on the spatial function. So that probability density doesn't depend on the time. That means if you have a wave function at a certain point, guys, the probability, now imagine here, this probability depends only on the point, this x value, x1 probability is a constant probability, it doesn't depend on the time, right? Unless this is an eigenstate, energy eigenstate. You might be wondering, so throughout my entire video series, I have been repeating this word eigenstates, eigenstates, eigenstates. But this is in next video, most of the time I'll be able to introduce what the other states are, right? So some states are not eigenstates, guys, in the sense when the collapse happens, you are not certain what that you are going to get. So but if it is an eigenstate, your outcome is certain, and your final equation, sorry, your final wave function, that your final energy is even a certain value, right? Don't worry about those stuff. This is just the surface, guys. We are supposed to dive deep into these concepts later on, but my point is now here x2, no, this can't ever be negative, right? So then anyway, probability density can't ever be negative. Now here, now at x2 point, that's always 0. At x3 point, this value. At x4 point, this value. It's like that, right? So all you have to understand is probability density now uh, doesn't depend on the time if it is an eigenstate, right? So now we have already identified what this time-independent Schrödinger's equation is, and we can deal with the spatial part, right? By referring to time-independent Schrödinger's equation. In the meantime, we can deal with the time-dependent section or time-dependent function, which is the a time function using this particular relationship. Thank you for joining this video, guys. And in next episode, I'm going to walk you through one-dimensional, I think 1D walls. This is, I think, now that's a favorable environment for us to learn 1D potential walls and even tunneling up to some extent I can introduce to you, right? Uh, yep. See you with the next fresh video. Have a good time till then, guys. See you.